I love a blue plastic. Yeah, it's a nerd updated look that I think is
So
very
this is
effective.
the
This is your clicker. Yep.
Okay.
It's been a little bit touchy. I think you pointed towards those guys. I think that's yeah. And feel free to adjust this. Everyone's. Ladies and gentlemen, we're going to resume our programming precisely at 1, so I hope you've enjoyed that delicious lunch, and I'd like to invite you all to come forward and take your seats again. We're going to be having some more fantastic programming this afternoon. Thank you. Team more sitting down the front if you'd like to come. We're ready to start the afternoon's programming. Okay, we have a fantastic speaker up for you next. It is my great pleasure to introduce our next speaker. Roberto Pieraccini is a former director and CEO of the International Computer Science Institute at Berkeley. He has worked at Bell Labs, he's worked at IBM, he's written a book, he's served as the chair of the IEEE's Speech and Language Technical Committee. Today, though, he's the director of Advanced Conversational Technologies at Jibo, maker of the world's first family robot. Thank you very much.
Thank you, Rachel. Generally, when you serve wine, since we are here, you start serving your best wine first because after that, nothing really matters, you know. So I have to say that the talks this morning were excellent. It would be hard to match the quality of these talks. And also, I feel really humbled being here with so many people who really change the world, at least our world of technology, and so many people who will change the world. So it's really a humbling experience. So, that's there. I decided to call my talk, The Future is Not What It Used to Be, and you'll discover why at the end. And Alex asked me to talk about the history of, the history of spoken language interface. You see, I saw the history because I started almost 30 years ago when I built my first speech recognition system in Italy. And then I worked at Bell Labs, AT&T, IBM. I worked for SpeechWorks, SpeechCycle, and now Jibo. So the reason, the reason why Alex asked me to talk about the history, because I guess he read my book, which is not a textbook, but a book about the history of speech technology, or the way I perceived it, from the early attempts to today. And like Dan before, I say it's a great book. You will enjoy it. You buy it for Christmas. And so, and another thing I want to, many people ask me what Jibo is. So I don't know if how many of you have seen our film. But we have been on Indiegogo. We have been very successful on Indiegogo for 2 months. We became the most successful technology campaign ever on Indiegogo. We sold for $2.3 million of Jibos. And I'll play a little movie for those of you who haven't seen it yet that explains very well what Jibo is. So I start from the future.
This is your house. This is your car. This is your toothbrush. These are your things. But these are the things that matter. And somewhere in between is this guy. Introducing Jibo, the world's first family robot. Say hi, Jibo.
Hi, Jibo.
Jibo helps everyone out throughout their day. He's the world's best cameraman. By intelligently tracking the action around him, he can independently take video and photos so that you can put down your camera and be a part of the scene.
Jibo, take the picture.
He's a hands-free helper. You can talk to him, and he'll talk to you back, so you don't have to skip a beat.
Excuse me, Anne?
Yes, Jibo.
Melissa just sent a reminder that she's picking you up in half an hour to go grocery shopping.
Thanks, Jibo.
He's an entertainer and educator. Through interactive applications, Jibo can teach.
Let me in, or else I'll... And I'll... And I'll blow your house in.
Hey, where'd you go? There you are.
He's the closest thing to a real-life teleportation device. He can turn and look at whoever you want with a simple tap of your finger.
Check out my turkey dinner, Mom.
I wish you wouldn't eat that.
Hey, they make turkey pizza? I want turkey pizza.
And he's a platform, so his skills keep expanding. He'll be able to connect to your home.
Welcome home, Eric.
Hey, buddy. Can you order some takeout for me?
Sure thing. Chinese, as usual?
You know me so well.
And even be a great wingman.
You have a voice message from Ashley. Want to hear it?
Absolutely.
Hey, call me when you're home.
Better make that takeout for two, Jibo.
We've dreamt of it for years, and now he's finally here. And he's not just an aluminum shell, nor is he just a 3-axis motor system. He's not even just a connected device. He's one of the family.
Good night, Jibo.
Jibo, this little bot of mine.
So, okay, now I stop with my personal promotion and I start talking about the history. So, the vision. What's the vision? Who recognized this movie? Okay. Metropolis, good. So, the vision is to talk to a machine, right? And of course, the most immediate things that we see when we talk and we understand our muscles that control our mouth and our inner ear that receives the vibration and transforms it into the auditory nerve. So that's actually things that we can measure. But there are many other things that we don't understand very well, like phonetics, morphology, lexicon, syntax, and then we make assumptions on that. And we've kept making assumptions for many years. And that's actually difficult part of building talking machines, a machine that understand. On the machine side, we have different technology. We have speech recognition, natural language understanding, dialogue management on the input side, and on the output side, speech synthesis, text-to-speech, and language generation. So all these technology contribute to building machines you can talk to and understand from you. Oh, too close, yeah. Is that okay now? Can you hear in the back? Yeah. So, so the technology started many years ago. Probably the first working technology about talking machine is what we call the voder by a guy whose name was Homer Dudley at Bell Labs. And the voder was actually a speaking machine controlled by a human, an operator, which was trained for 1 year. Practically, the operator did what today is done by the text processing in text-to-speech. Was asked to play a word or a sentence, and in his or her mind was translated into phonemes, and then using this keyboard to input the phonemes in the machine. This is how the machine sounded like. Oops. Can you click on the speaker? Yeah. No, on the little, yeah. Nothing's happening?
Will you please make the voters say for our Eastern listeners, good evening, radio audience? Good evening, radio audience. And now for our Western listeners, say, good afternoon, radio audience. Good afternoon, radio audience.
So this was probably the first electric talking machine. There were other attempts, probably the oldest one in 1791. This guy, von Campelen, built a machine with the bellows and the reed, and that was making sounds in approximating vowels and other consonants from languages like Italian and French. And they say German was a little bit more difficult because the German consonants are difficult. But anyway, so, but you know, speech recognition started a little bit later in 1952 when three guys, Davis, Bidus, and Balashek from Bell Labs, built a machine that could recognize digits spoken with pauses in between. And this machine was completely built with analog circuitry. They didn't have computers at the time. It was a room filled with vacuum tubes and resistors and impedances and capacitors. And the training was actually, they could go in there and tune the machine to different voice by using a screwdriver and changing some of the value of the resistors. It actually worked quite well. They report on the famous article that was written in 1952, report that had quite good performance for both male and female speakers. The idea of this machine was to, AT&T built this machine. They thought of, and they used this word, for affluent subscribers. They could dial by voice. But the cost of this machine was, you can imagine, they had to change tubes every 2 days to burn, and so it was never commercialized, like many things from AT&T. The actual pioneer was Jim Flanagan, who is still alive, and actually is the guy who hired me at Bell Labs in the 80s, who did something very, very interesting. He's the first one who thought that speech research could be done with computers. So today we take that for granted, but at that time it was not. It was 1960s, and the first one that brought the mini computer. This is an example of a Nova computer. We brought it to the lab, and it was a real pioneer. I think they used digitized speech. Since A to D converters were not very easy to get at the time, he digitized manually 10 words, looking at the oscilloscope and measuring the samples by hand and writing them on a piece of paper. So, and they used that for 10 years. They used these samples for 10 years. So there was really pioneering work in speech. And the people you see there are famous people. I think it's Ron Crusher and Larry Rabiner, who will have a big place in the history of speech recognition. The first speech recognizer had what I call the illusion of segmentation. So I think if you want to recognize speech, the first thing you think, remember the chain that I showed before, the phonetics, morphology, lexical, syntax. You say, oh, well, I take speech, I break it into phonemes, and then phonemes make words, and so on. But that didn't quite work. So this is speech. I think the sentence, my number is 7390274. And if you create an algorithm that breaks speech into phonemes, you can then put the phonemes together to create words, put the words together to parse the words, and then get to semantics of that. Unfortunately, what you do for that, you write rules. Right, and the rules, you write rules for the phonemes, you write rules for the words, you write rules for the syntax, you write rules for the semantics. But unfortunately, the problem is you get errors. Every time you try to recognize something, you can make some errors, and the errors propagate to a higher level, so you get more errors and more errors and more errors. So what you do, you write more rules, and then you get more errors, and then you keep writing rules, and the thing never converges. So that was the beginning of speech recognition. People could write some rules, and if you look at the composition of the teams in the 50s and the 60s, I was in kindergarten there, they didn't hire me, but at the time. But there are a lot of linguists, and a few computers. Well, there's no computer science as we speak today. There are some computers, but a lot of linguists that were writing rules, and there was this concept, AI concept of expert systems. So speech recognition was an expert system, extracting the rules and putting them in a digital form in a computer. So why speech is difficult? Speech is difficult because of all these elements that are in speech. Intra-speaker variability, nasal verbalization, co-articulation, constant dependency, word confusability, word variation, speaker dependency, multi-interpretation, limited vocabulary, ellipsis and anaphora. So all these things make speech difficult. And all these things are those that need to be handled when you build a speech recognizer. So there was a winter, like every good technology, even speech recognition had a winter. Like there was, AI had like probably 3 or 4 winters. Speech recognition winter was in 1969 when a high-ranking director at Bell Labs wrote an article on the Journal of the Acoustic Society of America called With Their Speech Recognition, where he said that trying to build a speech recognizer is like trying to sell soap or something like that. So he didn't believe that speech recognition would have any value. And the problem that John Pierce was also an advisor to the government to the ARPA projects. So he really froze all the projects in speech recognition for a few years. But in spite of that, in 1971, ARPA created a project called SUR, Speech Understanding Research, that posed the foundations of modern speech recognition. Now, the guy you see there is Raj Reddy, who was Dean of the Computer Science Department at Carnegie Mellon. I think now he's retired, who really, Raj is a smart guy, and he wanted to hedge his bets in this project. So he had 2 systems. One built with traditional AI was called here Say2, and one was built with engineering approach, was called Harpy. And many other sites built system, all of them built with traditional AI. So rules, errors, so rules. And these are the performance at the end of the project. So a company called SDC built a system that had 24% accuracy, whatever accuracy was defined at the time. BBN built something called Hear What I Mean, HWIM, which had 44%. CMU Hearsay2, heavily based on the AI approach at the time, at 74%. And this new system called Harpy had 95% performance. And Harpy was considered a stupid system. Why? Because it worked on simple network. So this was Hear What I Mean, HWIM. So you see very complex knowledge base. There are all types of knowledge represented in different forms. It was island-driven parsing. It was very, very sophisticated. While Harpy was a stupid network that represented all the possible ways to pronounce all the words in the language. And they used a dynamic programming algorithm to find the best match in this network that matched the input sentence. And that won that was the best system, by far. The lesson learned is that at that time was a hand-built knowledge does not scale, and the engineering approach, the brute force approach, the stupid approach, that's how people called it, or the ignorance-based approach. And with the global optimization criteria, wins. And that brought the next wave of systems, which are based on pattern matching, engineering approach, and statistical we'll see in a minute. But I want to play for you what I call vintage speech recognition. So this is a movie, a film from Carnegie Mellon. You recognize, if you know him, Raj Reddy, very young here. And was probably the AI, he talks about the AI-based system. And look also at the way some of the characters in this film look like. Is Raja ready?
Let us now look at the performance of the system in a couple of other task domains, news retrieval and medical diagnosis.
Tell me about war.
You can imagine which period of the United States was that, right?
When completed, the system will respond with all the news stories of the day
But all
about
the
war.
time it takes to come up with an hypothesis.
Tell me about Nixon.
Of course. Nixon didn't say the famous sentence yet.
Here we have another example of an error resulting from inadequate knowledge at the acoustic phonetic level. The word tell is mistakenly identified as give.
So this, now we talk to Siri, we talk to Cortana, and we take speech recognition for granted, right? That was speech recognition in the 70s. Actually, by the way, since I give so many demos with speech recognition, typically, speech recognition does not impress people. What impress people is more the speech that come out, like the text-to-speech and the voice. It's often recorded voice, right? Because, oh, wow, it talks very well. So there was, and I believe that the complexity of text-to-speech and the complexity are similar. It's not that talking is easier than recognizing. But there was a guy, which I don't mention the name, that pissed off the whole text-to-speech community by going to a conference like this and taking a toothpaste tube and spraying the toothpaste out. And say, this is text-to-speech. Putting the toothpaste inside the tube bag is speech recognition. I don't believe this is true because yet today we don't have a text-to-speech that is comparable to humans. So, and also an interesting thing, if you go back to the science fiction, there are different things. So if you go, Isaac Asimov, I, Robot, it says explicitly that the first robot built by I don't remember the name of the robot corporation, they could understand speech very well, because understanding speech is very easy, as you all know, but they couldn't talk well, because talking is much more difficult. On the other hand, the day the Earth stood still, which is a very old movie, this tin can robot that is, I don't remember the name, Klaatu, doesn't say a word in the old movie, but he understands speech very well. When his master tells him to do something, he goes like that. So the notion that talking is more difficult than understanding is still there. And we know that when we give demo, that's why we use very beautiful voices. And then people are ready to forgive the speech recognition and doesn't understand all the time. So then dynamic programming came out. I'm not going to explain what dynamic programming is, but it's a way to search in a big space of possible hypotheses of what the word that people said was in a very economical way, in a very computational economical way. So it was invented in Russia first, apparently, by a guy called Vinciuk. In fact, for many years, I remember at the beginning when I read that, many people were calling it the Vinciuk algorithm. And then at the same time by two Japanese guys, Sakoi and Chiba, pretty much at the same time. There are questions whether Vinciuk went to the conference in Japan, he heard, or Sakoi and Chiba went to a conference in Russia and they knew about that. But no one knows about that. So, and then we went from isolated word to speaker dependent, so only one speaker could talk, the speaker who trained the speech recognizer, to connected words, so speaker independent, and then subword units. That means you can build any vocabulary instead of recording templates from every possible word. Because the original way to do speech recognition was recording examples of every word and then chaining the example together, to find what the best matching with the input utterance was. Now, there was something, actually, Adam, you call it the statistical revolution or something like that, right? And there was actually a revolution. If you build a template-based speech recognition, which I did in my first years in speech recognition, then the step to statistical could be very, very intuitive. They say, well, templates represent points in a distribution, then why don't we represent the distribution instead of taking these random points, right? And that's what, of course, the math was not very easy. So the contribution, there were two people who really contributed to the modern speech recognition. One is Jim Baker or Fred Jelinek, who unfortunately passed away a few years ago. And they're, I believe, the fathers of the statistical revolution. Yeah. So Jim Baker was spending his summer months as a summer student at the IDA, the Institute for Defensionality in Principle, where there was a famous mathematician called Leonard Baum, who will invent the Baum-Welch algorithm. It is the key to learn statistical models of speech, which are called hidden Markov models. Then Jim Baker was hired by Fred Jelinek, and there is a nice story that I would like to tell. And then Jim went away from IBM, created Dragon, and we know the history, right? One of the first things that people from IBM said is no data like more data. And I think that was Bob Mercer was mentioned in one of the previous talks. It means the more data you have, the better performance you have. But before that, there is a sentence attributed to Fred Jelinek, and they say, whenever I fire a linguist, our system performance improves. And the story behind that is this. Personally, Fred told me the story. There were two teams competing at IBM in the late 60s for speech recognition. And actually, the manager of one of the teams, it was more AI-based, knowledge-based, was also the manager of Fred Jelinek. Fred Jelinek was more an engineer. And they wanted them to build on a very restricted language. It was called the Rayleigh language. It was very finite state language. They wanted to build a speech recognizer on that, and they forced the other team to do a language-based, knowledge-based approach. And they got performance in the 50% accuracy. Then, according to Fred, this guy, who I think I know who he is, but he never mentioned his name, lost interest or left or was fired. We don't know what happened. But so they started to build their statistically based speech recognizer. And immediately, the performance jumped from the 50 to the upper 80, right? So they say, well, we are still using some linguistic information here. So we use the phonetic transcription of every word in the language. And that's not fair. We want to show that even if we don't use any linguistic information, the recognizer works well. So instead of using the phonetic transcription of every word, they use the orthographic transcription, which in English is very far, most often, from the phonetic transcription. So they have models for the letters of the alphabet, and they wanted to use this model to recognize speech. And guess what? Their recognition performance were still better than the one built by linguists. So Fred said, well, anytime I fire a linguist, my performance will go up. But when he became a professor and the head of the department at Johns Hopkins, he started working on putting more linguistic information in the statistical systems. So he gave a talk when he accepted a lifetime award at one of his conferences, and the talk was called "Some of My Best Friends Are Linguists." So he tried to bridge the gap between the purely statistical and the linguistic-based speech recognizer. So, but hidden Markov models, which is the technology on which modern speech recognizers are based today, but it didn't come out of IBM. So IBM built a lot of recognizer. I remember going visit IBM in the 80s and having Bob Mercer showing me their transcription system. But their papers were very hard to read, and they didn't put a lot of details. So, and there were a couple of key details that if you didn't know how to do that, you couldn't build a hidden Markov model recognizer. And Larry Rabiner from Bell Labs figured out those details and wrote what I call the bestseller paper in speech recognition, a tutorial on hidden Markov model and selected application in speech recognition, which was published in 1999. And that signed the widespread use of hidden Markov model. Anyone who read this paper could build a hidden Markov model-based system. And today's technology is still based on many of these ideas. Now, I want to show another movie, which is really funny. So people started to do other things with speech recognition and started thinking about multimodality. That's a thing we do today. Like, we're thinking of, on the iPhone, you can touch, you can talk, you can type, and so there was a project at MIT in 1979 called Put That There, and the person you see here is Chris Schwant, who's still working at MIT Media Labs. It is a demo. They had a demo room where you can talk and you can point with a laser pointer, and you can interact in these two modalities. It is an interesting movie.
Create a blue diamond there. Move that there. Put that there. Move that below that.
Not very useful, but it's interesting.
Move that west of the diamond. Create a large green circle there.
Green circle.
Oh, shit.
Well, you know, we all experience speech recognition that doesn't work. Yeah. So anyway, so I think around the late 80s, we had another winter of speech recognition, which this time I lived through. I was there, where we believed that we couldn't really do speech recognition for any practical application. The performance were not great, and yeah, we could do something, you know, but we are a little bit depressed about the performance. I think it was a kind of worldwide feeling, right? And what happened at the time, around 1988, DARPA, at least in the US, started launching into project, pretty much the one that Adam said about Kalo. You know, there was speech recognition projects where the rules were very clear. You get the funding only if you get good performances. So, every year there was an evaluation. An evaluation, you bring your system. It was a blind evaluation. You get, for example, for speech recognition, you get a bunch of files with audio files, and then you had to tell the transcription. You had not enough time to do them by listening and cheating. There was no time to cheat. So at the time, I was at Bell Labs at the time, and the computers were like burning, and people were shouting at each other because they used too much CPU, because the evaluation results are due at the end of the week. And then you're just crunching number all the time, hoping to have the best performance. And if you didn't have the best performance for a couple of times, you are out. Right? So that's what the result of that. There are two results. One of them, you see all these curves. Every curve is a project. For the first one was called resource management, and it was the one that really changed the view on speech recognition. Resource management was a very simple task, 1,000 words with a very artificial language about military resource management. Put all my ships to the north of the Gulf Sea, or this something like that. Not very interesting but all these sentences were created from a very simple finite state grammar. Everyone started competing on that. And what happened, since every year we had evaluations, and we had results and papers on that. People started to push the limit, and you see the performance, this error rate, go down. So the first, I don't think there is a laser here, but the first curve, the black curve on the left, the error rates go down, go down, go down. Then people get very cocky and say, oh, we know how to do speech recognition. Let's do something more difficult. And something more difficult, what happened? The performance go back to horrible error rates again. People start tuning the recognizers, and the performance go down. The error rate goes down again. And then say, okay, let's do something more difficult, like from red speech to spontaneous speech, from spontaneous speech to conversations, from conversation to command and control of databases, and so on, to meetings, and the performance jump. You know, for instance, conversational speech, you see the top almost 100% of error. No, not there. Yeah, there almost 100% of errors. It's called switchboard, the red curve that goes up to the top. At the beginning, everyone had like 90% error rate. What do you do with 90%? I remember people arguing between 70-74% error rate, and at one of these meetings. And it was really terrible. And in some work, people brought the performance down. So the problem, sorry. Oh, sorry, I was going the wrong direction. So one of the problems is that, so one of the effects that everybody improved that, but the improvement was mostly by tweaking. Tweaking on this, there's nothing really new. At the beginning, actually, there was a guy whose name is Kai-Fu Lee, and it's what I call the Kai-Fu Lee phenomenon. So he was a student of Raja Reddy, and he was a fantastic engineer. He read all the papers on hierarchical models and took all the algorithms and the tweaking that people had done and put all of them together in a very obsessive manner, showing what improved and what didn't. And he got something that was very good. And then everyone started to follow Kai-Fu's example. And we started getting better and better performance. The problem with that was, and it's still a problem today in the DARPA community, still having things like that in the DARPA community, is what they call the loss of biodiversity. At the end of a program, everyone was doing exactly the same thing. Why? Because since my grant is at stake, I will do what works better. And someone else in another company does something which is good, I do the same. And then all this recognizers looked alike at the end. So what happened is two very interesting things. People who were joining this evaluation were people from SRI and people from MIT. And I used to meet Mike Phillips, I used to meet Heimer White, all these people were there. And these people decided, say, why do we do for the government? Don't we start a company instead? It's going to be much more fun, and maybe we can do it commercially. We can make money with that. And there were two spin-offs. One was called Nuance, and one was called Speechwork. And I'm sure some of you here are part of this history. And these two, I believe, that they started this spoken dialogue industry. There was mid-90s, and these two companies were extremely big enemies. I work for Speechworks, and we took, people from Nuance, terrible. And I'm sure people from Nuance were saying the same of us. There was, I think Ron is here, but it was terrible at the time. But we loved each other, but we hated each other, right? There was a very interesting time. And then, of course, at the end, you see the end, and you probably know the end, right? So that created a whole industry, a whole ecosystem, which I will talk about in a few minutes. But what about language understanding? I will say very few words about language understanding, because I also was, part of it. So one way to do language understanding is to use grammars. And grammars, you write a grammar, and you put some tags here and there, and then you get the semantics. Everyone can do that. Certain people, and I was one of them, decided, well, why don't we use statistical method? They're more intelligent, right? We have data, we can learn semantics from data. And that was 1991. And we built a system based on something we call conceptual data Markov model. I believe was the first one, based on statistical semantic understanding. Other people, still Bell Labs, Algorithm built How May I Help You, which is semantic classification. But the idea is that you get sentences, you transcribe them, you attach some semantics to them, and then you learn that. You learn how to do that on sentences you have never seen before. So the generalization power is much, much bigger than what you have in grammars. That was a trend that today is quite interesting. David Sunderman, who is sitting here, and I, a speech cycle, we decide, when you build a speech system, you still use some grammars, like for yes, no. And I'm talking about big speech systems that are on the telephone network that you talk to for customer care. You just know, use numbers. And then we had the idea, say, why don't we just get rid of all the grammars and we use all statistical systems? And we could do that, train them automatically. Actually, we could train them online while the system was working. We had the whole system to do automatic transcription. The only problem was our colleague Victor, who was in charge of operations. And if you know people operation, they always have to push a button to make things happen, and he was not happy. So we couldn't convince him to push the grammars automatically. So there was the only manual thing, it was Victor pushing a button when we told him this grammar works better than the other. But everything could have been self-learning, automated, and we were very happy about doing that. So dialogue is another interesting thing, right? So the way to build dialogues still today for large systems is to build large workflows, which is called call flows. And actually, people are getting very good at that, right? So, and that there are tools, and we'll talk a little bit about the tools later, that allow you to build extremely sophisticated call flows. One thing that I did in my research years was to think about dialogue system like a game. Like if you play chess, chess is a game. You know a few rules, and if you keep playing, imagine people who are in a prison, and they play against themselves. So say, okay, I move this, and then go to the other side. Now I move this. Actually, they learn a lot, because they start with the rules of chess, or backgammon, or anything. And then the user enforcement learning procedure. We humans use reinforcement learning. So anytime one of the two players, which probably is the same player, because they're in prison, wins, say, oh, I did something smart here. Let me review my moves. Oh, maybe that move was smart. Let me just do it more often. Or maybe generalize to a certain strategy or something like that. So dialogue is the same thing. And then dialogue, you can cast the problem of dialogue into what is called a Markov decision process, which is a very interesting mathematical way to represent this type of process. And you can use reinforcement learning algorithm to learn why it's talking. Unfortunately, the problem is that you need millions of dialogues to learn a dialogue. And you could, we demonstrated that, but it takes a lot. So we did, and people did, something very approximated of that. So we just put very simple changes in an existing dialogue, and we just optimize or adapt the dialogue. Today, it's a whole discipline called statistical dialogue systems or machine learning dialogue system, and the leading abstraction is called POMDP, which is partially observable Markov decision process. So when you put an uncertainty of certain inputs like speech recognition in that, then the math starts to become complicated, and there's still a lot of work to do, and it's a very academic, still very academic discipline. But now let's talk a little bit more about the business of speech. So very quickly.
Hello, and welcome to Movie Phone. If you know the name of the movie you'd like to see, press 1. Come on. Using your touch-tone keypad, please enter the first 3 letters of the movie title now. You've selected Agent Zero. If that's correct, press 1. What? You've selected Brown-Eyed Girl. If this is correct, press 1. Why don't you just tell me the name of the movie you selected? Channel? To find the theater nearest you, please enter your 5-digit zip code now. Why don't you just tell me where you want to see the movie?
Lowe's Paragon, 84th and Broadway?
Channel is playing at the Paragon 84th Street Cinema in the main theater at 9:30 p.m.
Yeah, now I got you.
It's also playing in theater number 2 at 9 o'clock.
So, but practically the idea of the business, or the beginning of the business pitch, is why don't you just tell me, right? We had all these clunky systems, press 1 for this, press 2, why don't you just tell me that? And then there was an evolution, it went on and on, I don't want to. So another important thing was the life cycle. So people started building applications not like in academia, that more like a work of art, but it's a business application with an engineering process. So there were design specs and the profession of voice user interface design, we have some of them here, right? Came from that, the whole profession that is still very active and so building the voice user interface. So and building tools. These are tools built by me and my team at Speech Cycle that allow you to build extremely complex dialogue systems. I would like to skip that. The ecosystem grew, so there are a lot of people, a lot of industries around there. Not only the voice user interface industry, but there is the platform industry, the dialogue management industry, and so on. So this is the ecosystem of system on the phone. Now, we are used to this type of systems, right? When you talk on the phone. And I would like to compare the 2001 vision of a computer to actually 2001 computer speech. So this is a famous movie called 2001: A Space Odyssey. Most of you have seen it. And there is one of the most dramatic scenes in when the astronaut, David Bowman, wants to go back to he's in a pod, wants to go back to the spaceship, otherwise he will die because there is a limited supply of air in the pod. And the computer, HAL 9000, denies that. I just played this little clip again for you. Oh. Can you play the clip? Okay.
Hello, Hal, do you read me? Hello, Hal, do you read me? Do you read me, Hal?
Affirmative, Dave. I read you.
Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What's the problem?
I think you know what the problem is just as well as I do.
What are you talking about, Hal?
This mission is too important for me to allow you to jeopardize it.
I don't know what you're talking about, Hal.
I know that you and Frank were planning to disconnect me. And I'm afraid that's something I cannot allow to happen.
Okay, now the leap of imagination I want you to make is what would this conversation sound like if actually HAL used the technology of 2001? And I did that, oops. There should be a audio clip there, somewhere outside the, probably this is the difference between Apple and now if you just close the presentation mode, there should be a clip outside the slide, yeah. Go into editing mode, yeah. Okay.
Hello, Hal. Do you read me, Hal?
Yeah. No video, so it's fine. That's fine, yeah. Can play it? The video is not important. There is no, just the audio. Yeah. No, forget about the video. Just play the audio, like you did before. Coming up? Okay, leave it like that.
Hello, Hal. Do you read me, Hal? Welcome to Hal. Please listen carefully, as my options have changed. You can say, open the pod bay doors, play chess. Open the pod bay doors, Hal. Sorry, I didn't understand. You can say, open the pod bay doors, or press 1. Play chess, or press 2. Learn the Alp horn, or press 3. Around what time would you like the pod bay doors to open? You can say, today, tomorrow. Now, damn you! Main menu. Please listen carefully, as my options have changed. You can say, open the pod bay doors, or press 1. Play chess, or press 2. I'm really sorry. Even though your call is really important to me, this mission is even more important, and I cannot allow you to jeopardize it. I don't know what you're talking about, Hal. I know you and Frank were planning to press 0 for an agent, and I'm afraid that's something I cannot allow to happen.
Go back to the presentation. Yeah, so this was fun. You know, I really have to. You know, this was my idea, but the realization was my friend Jonathan Bloom and Peter Krog. You know, actually, the voice is Peter Krog, you know, but some of you know him. So yeah, that was the reality, and so I would like to show you this history of the speech industry portrayed by Mike Phillips. Mike Phillips was the founder of SpeechWorks, and so he has been in the industry as long as me, so he knows everyone. And you know that, I think it's just a funny slide. So these are the, in 1985, probably there are some omissions here, but you know, the players in speech recognition were IBM, Dragon, Kurzweil, BCS, Scott Instrument, and VPC. Now there was mergers and acquisitions, and so there were more players, Microsoft and Pure Speech, Philips, ATI. SpeechWorks started, Nuance started, and then there were a lot of acquisitions, and everything consolidated, and eventually it became that, right? So that's, this is 2005. Now today probably it's a completely different view, but the market is quite consolidated. But 2005, the last 5 years, what happened in the last 5 years? Cloud-based speech recognition took over, and there were many companies, Blingo, Pronto, but most notably Siri and Google Voice Search, or Google Now, Google, OK Google. And this really changed the outlook of speech industry. And I'm not going to talk about this because, I mean, Adam gave a fantastic view of Siri, so you know about that already. But from the technology point of view, there was something that happened a few years ago, which is called deep learning. And apparently, either this is hype or not, but the results are real, and there is a big change in the performance of speech recognizer. And this is due to a veteran of neural networks, Jeffrey Hinton, who wrote a paper with one of his students, Salakotnikov, in 2006, about deep learning. Practical deep learning is like using neural network with a lot of hidden layers, and they found a way to train this, and they got interesting results. So this is a little film that Google shot and came out a couple of weeks ago, And I took the clip from actually Jeffrey Hinton, who was hired by Google, talking about deep neural networks.
So until quite recently, people got features by hand engineering them. They looked at sound waves and they did Fourier analysis and they tried to figure out what features should we feed to the pattern recognition system. And the thing about neural networks is they learn their own features. And in particular, they can learn features and then they can learn features of features and then they can learn features of features of features. And that's led to a huge improvement in speech recognition.
Yeah, so if you look at conferences, I mean, 3/4 of people who are working on speech recognition today works on deep learning and deep neural network. And whether there's hype or reality, we will see that in a few years, but there's a lot of work on that. And practically, what's happening, so this was an old model of human speech perception that was in 1986 by McClelland, was called the trace model, where different levels of knowledge, the one we saw at the beginning, like phonetic, acoustic, phonetic, morphology, and so on, were represented by different layers of a neural network. The only problem, people didn't know how to train all these layers. Today they know. And what's happening is that while, until deep learning, the deep neural network, we put very little emphasis on the front end, the feature extraction, and a lot of emphasis on the search, doing a lot of complex things like having a large number of models, huge number of models, and so on. Today, with the introduction of deep learning, you put a lot of emphasis on the front end that you can learn automatically using in smart algorithms. And the search becomes so simple that, like my friend at IBM say, everyone can do it. Yeah. So deep neural network made speech recognition much, much simpler because all the complications are taken care of by discovering features automatically using neural network. So this is my last slide. I try to ask myself this, and this is why the future is not what it used to be. If you ask me in the 80s, what do you think speech recognition capability will be in 20 years from now? And having a scale that goes from nothing to human-like capabilities. This is what I would say, 20 years from now, it will be like human-like capabilities. Then if you ask me again in 1990s, I would say, well, speech recognition doesn't work. I keep working on it because it's an interesting problem that guarantees I have a job, but it really doesn't work. If you ask me again in the 2000s, it's better. We had the HAL 9000 thing. I'm sorry, I don't understand that. Can you repeat that? Yeah, we could build applications. We are not very happy with that, but we could build very interesting applications. The 2005s, yeah, pretty much the same. We could build the same application, maybe build them better, faster, and cheaper, but nothing really changed. If you ask me today, I would say that very soon, 20 years from now, we will have human-like capabilities. We already have in some applications. So this is the future. Our future changes with our experience of the present. So lesson learned in all this history. There is no data like more data, of course. A speech system is good as its interface. So you can build a very good speech system with a crappy interface, and the system is crappy. Don't do by hand what you can learn. Don't discover features by hand. Don't put rules by hand. The more you can learn, the better the system is. And at the end, the system will not be anthropomorphic. We'll have a completely different idea of what speech is than we have, but it will perform much better. And finally, we can really make prediction. And I was surprised by Apple that predicted in 1987 that Siri will come out in 2011. Yeah, but that's Apple. So that's it. That's my talk. Thank you. Yes. way the way I put it, maybe I'm not working, I've not been working on the network for decades, so I just see what's happening, and I don't do so, and I'm totally wrong. It's a way to build an intermarker model and dress it up as an internet. It's a way to put time, because to put a notion of state. So the recursion, you have state. Yeah, that's my way. But I might be totally wrong, because I'm not working on this field anymore, yeah. Other questions? Yes? Oh, so the question is, in 1988, there was a cover of a magazine saying that speech is the next big thing. What will happen in next? What is the cycle after now? So I have another slide that I didn't have today with quotes from Bill Gates about speech recognition as a big thing, and there are probably 25 of them every year, and every year say, the next 5 years, speech will be a big thing, and every time, so speech will be a big thing 5 years from now, and that was the same thing for 25 years. Yeah, but there's a big substantial change today, and the change is the fact that two changes. First, if you take the IVR system, we built system that no one wanted to talk to, and that was very important. I remember going to a party and say, I built this fancy system and people didn't talk to me anymore after that. It was a completely turned off. So today, people like to talk to Siri, like to talk to I hope they would like to talk to Jibo and so on, right? So that was the thing. And the other thing is ubiquitous. Yeah, so these are the big changes. Yeah. So. Yeah. 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 Yeah, I mean, it's very important to take it into account. You design for children in a different way, you design for adults or for seniors, right? So I believe a voice interface has and will continue to have an important role. We will have better tools to do that, and you don't have to build all the states, but maybe you can teach the machine what to do in a different way. But yes, demographics is very important. In a way, yes, but there are a lot of tools that help the manual process. Yeah. 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 So the question is, how do I see the Internet of Things, not including the cloud, and what is the role the speech will play in Internet of Things? How the Internet of Things improves speech recognition? I mean, I think there was a discussion in the panel about the fact expectations and stuff. I believe that if we know what we are talking about, speech recognition works better. So if I know that I have to switch a light on, and I can say light on, and I know probably 25,000 ways to say that, speech recognition will be much better. Then there is a problem of far field. Internet of Things, you don't talk to things, but you talk to the room. So, but there, we know today there was an announcement by Amazon with this little thing that has microphone arrays and stuff. So there's a lot of technology to improve the performance in far field, and so I think that if we know what we want, speech recognition can be much better. Yeah. Yeah, sure. Oh, yeah. Yeah, that's actually a very, very crucial problem for my company, for Jibo, because Jibo is hands-free, and you can talk to Jibo from 5 meters distance. So today there are ways to train the models using noise, to do cross-training for noise and acoustics, and to make them more independent of noise. Plus, using microphone arrays helps a lot because you can really beam you can use beamforming, you can beam on the voice of the speaker. You know. If I see, excuse me? Yeah. Yeah, it's noise. It's a reverberation. Reverberation is a very important thing. It's a difficult thing. So one of the notion in speech recognition is that speech recognition works well in matched conditions. So if you train speech recognition in noise and use it in noise, works very well. But if you train in clean speech and use it in noise, works well, and vice versa. If you train in noise and use clean speech, so these are the issues. You know, typically what you do, you use this noise in very intelligent ways and take into account all these notions that we have about using noise. Yeah. Thank you very much. Thank you. Thank you.
Thank you, Roberto. That was amazing. I'm really excited about this next session. We're going to have 3 developers showcase apps they've built around speech